Okay, so good day everyone. So welcome to Fluid Mechanics. By the way, I'm your Professor Engineer Ernesto B. Lim Jr. I'm a registered civil engineer at the same time a registered master plumber and also a materials engineer 1. So let's begin. So these are our chapter objectives. So first, describe fluid mechanics. Second, contrast gases and liquids by describing similarities and differences. Third, differentiate units and dimensions of measurements. Fourth, convert units from one system to another. And our last objective is to verify dimensional consistency of an equation. So introduction. So we'll define what is mechanics. Okay, so mechanics is the field of science focused on the motion of material bodies. Mechanics also involves force, energy, motion, deformation, and material properties. So when a material body is in the gas or liquid phase, the discipline is called fluid mechanics. So what is a fluid? So a fluid is a substance whose molecules moves freely past each other. So a fluid is a substance that will continuously deform, that is, flow under the action of a shear stress. Okay, so regardless how small that shear is, when that shear force acts on the fluid, then it will continuously deform. So both liquids and gases are classified as fluids. So liquids and gases. So this section describes liquids and gases, so emphasizing behavior of the molecules. So this knowledge is useful for understanding the observable characteristics of fluids. Liquids and gases differ because of forces between the molecules. So a gas is a phase of material in which molecules are widely spaced. So molecules move about freely and forces between molecules are minuscule except during collisions. Alternatively, a liquid is a phase of material in which molecules are closely spaced. Molecules move about freely and there are strong attractive forces between the molecules. So this will be illustrated maybe at our next slide. So this is the illustration for us to differentiate solid, liquid, and gas. So in here, as we can see, there's attribute here. Then the typical visualization. So this is a typical visualization for solid. But we are more concerned on liquid and gases because we are talking about fluids. So this is liquid. Now closely spaced but not very close. Then this is gas. Okay, so the macroscopic description. So for liquids, take the shape of the container and will stay in open container. Okay, while gases expand to fill a closed container. So mobility of molecules, liquids typically flow easily even though there are strong intermolecular forces between molecules. Okay. So for gases, molecules move around freely with little interception except during collision. So this is why gases expand to fill their container. So that's the difference. Okay. So because of the spaces, no, as we can see on the illustration, so it is only in or during collision that these molecules will interact with each other. Okay. So typical density. So for liquid, the typical density of water is 1000 kilogram per cubic meter. For air at sea level is 1.2 kilogram per cubic meter. So molecular space for solid, that is very close. For liquid, molecules are held close together by intermolecular forces. So for gases, so there's a large space between them. On average, molecules are far apart, so as we can see on the illustration. So effect of shear stress. So for solid, it produces deformation. So this will be discussed more on the materials of mechanics. While in liquid, so it produces flow. It produces flow. Also in gases as well, it produces flow. So effect of normal stress for liquid produces deformation associated with volume change. Then that has the same effect with gases. So viscosity. So for liquid, there's a very high viscosity rate, decreases as temperature increases. For gases, low, increases as temperature increases as well. So this viscosity topic will be discussed more on the property of fluids later. So about the compressibility. So for liquid that is difficult to compress because of its bulk modulus of elasticity, or bulk modulus of liquid of water is 2.2 times 10 raised to 9 Pascal. While for gases, it is easy to compress, okay, because of its low bulk modulus of gas at room conditions is about 1 times 10 raised to 5 Pascal. Okay, so that's all for part 1.